not stream.
Yeah.
That would be live.
I have trouble getting YouTube too.
It was streaming for a second. Alright. Low quality will do.
These are all scenes from the game, obviously.
Okay. That's me.
All right. So. And so the students who are responsible for this creation are Ben Anglin, Roger Hughston, and AJ West, and they will be presenting for us today this project. But in addition, we have a special guest, David Rose from Walt Disney Studios, and David has graciously consented to present to us today. And the reason he is significant in this project is because David is responsible for what is called a game engine. The game engine is named Panda 3D, and Disney recently released Panda 3D to the open source community, and it is now maintained between Disney and Carnegie Mellon University. It's one of the premier up-and-coming game engines that's beginning to be used in the open source community and in industry. So our program for today is, first we will have David give us an overview of Panda 3D. Then we will have a description of the project by the seniors, and we anticipate that these presentations will last until about 10 minutes before the hour, at which point, if you have a class you need to go, feel free to do so. But we have this room the following hour, so we're going to use the remaining time from 10 till the hour until whenever we want to have a Q&A, question and answer, and then we'll have some computers down front if you want to come and try your hand at the game. You'll be welcome to do that. So let me tell you a little bit about David Rose before he comes and gives his presentation. He's a native of Florida. He studied at Florida State University, and interestingly, because Pepperdine University is a liberal arts college, David's degree is actually in English. And he has done graduate work in computer science as well. He joined the Walt Disney VR studio in 1996. At that time, they were focused on medium-scale virtual reality attractions. And the projects that he has worked on include Aladdin's Magic Carpet Ride, which is a head-tracking, head-mounted display experience, Hercules in the Underworld and Pirates of the Caribbean, Battle for Buccaneer Gold, and both of those are stereoscopic cave-based experiences. And these were all built on a 3D engine that they had developed in-house using SGI Performer. SGI is Silicon Graphics. I don't know if some of you old-timers remember that company. And I'm not sure if they're still in business. Are they? They're still around.
Still around?
They're hanging on by fingernails.
Yeah. And beginning in 1999, they foresaw the end of SGI's dominance and began the effort to rewrite their 3D engine for personal computers and other platforms. And so Dave led the development effort of this new engine, which became Panda 3D. During this time, they developed Toontown Online in conjunction with Panda, and eventually they decided to release Panda as an open source project, enabling the partnership with Carnegie Mellon. More recently, they developed Pirates of the Caribbean Online with Panda as well. So please give a warm Pepperdine welcome to David Rose.
appreciate the attention, and I'm looking forward to seeing Ben and Roger and AJ give their presentation, because it looks like it's going to be a good game. As Dr. Warford explained, I was involved in the development of Panda 3D, which is a game engine that these three gentlemen have used to develop their own game. So I wanted to get a little bit of context behind Panda 3D and tell you a little bit about where it came from and where it's going. And I wanted to tell some, too, about how it can be used to make a game. That's one of the questions I get asked pretty often is, I've got a game engine, how do I make a game with it? So I'll start with a little history of Panda 3D and where it came from and where I came from. And it all begins with the Walt Disney VR Studio. This was a part of R&D back in the early days of the 90s in Disney. And of course, virtual reality was a pretty exciting thing in the 90s. Everybody thought it was going to be taking over the computer graphics world, and pretty much going to be everything that you ever saw in the future was going to be virtual reality. So back in those days, we had $1 million computers, and we used them to generate all sorts of fancy effects for their time. But because of that, because we were the group that was working with this expensive hardware, we were one of the few groups at the time that had any experience with 3D interactive computer-generated graphics. So the VR Studio has some of the longest term experience in 3D graphics because of this. Now technology's changed, and now you get 3D graphics on your pocket watch and things like that. So it's not quite so expensive anymore.
Yeah.
So we've spun a little bit to move with the times, and now we've parlayed our experience into developing massively multiplayer online games, which is some of the more technically challenging games to develop, and still tends to use 3D graphics. So I think we've made a pretty good transition there. Incidentally, the VR Studio doesn't technically exist anymore as a unit. We're part of the Disney Interactive Media Group. But we have a good imagination. We like to think like this. This was one of the early installations. This is a picture of the Aladdin's Magic Carpet Ride installation. And you can see in this attraction, people would ride on these motorcycle-like things, which are actually magic carpets, which look like magic carpet you see you put on the head on a display there. This is what we call gator vision, or the duck vision. And it's this is before the days of flat panel screens, so these actually had tiny little CRTs, which is why they're so big. And they're pretty heavy, and they had counterweights, but you put them on your head and look around in the world, and suddenly you're in the world of Agrabah. And you have 4 people together, they ride each ride their own magic carpet, and race together through the streets of Agrabah, trying to rescue the genie, and have a great time together. Turns out that magic carpets, you steer them very much like you steer motorcycles. And another one that we did back in the day, this is the Pirates of the Caribbean Battle for Buccaneer Gold. This is another virtual reality attraction, but instead of taking on a display, there's projection screens all around. This is what we call a cave. In this one, there's a physical set piece. There would be 4 people who climb into this physical boat, and 3 of them would man the cannons, physical cannons all around, and they'd shoot at virtual targets off into the virtual ocean. One person would man the helm, and he'd steer the boat around. Now, as I said, there's screens all around. You can see just 2 of them in front of you here. It's a little blurry in the picture because actually it was a 3D view. You had to wear special 3D glasses to see it properly, which made it more immersive and brought you into the world even more. That was a pretty popular attraction. In fact, both this one and Aladdin are still in operation, as far as I know, in Orlando. If you go to a place called Disney Quest, you can go play them, even though the rate's over 10 years old now. Now, nowadays, of course, we have our online games. So instead of having to go to Orlando to play these games, they come to you. Toontown Online has been around for a while. Pirates of the Caribbean, a couple years old. Both of these have very different looks, as you can see. But they're both MMOs, massively multiplayer online games, and they all involve lots of people playing together in the same world together. One of the things that these games have in common with each other and with the 2 games I was talking about is the 3D technology. They're basically doing the same sorts of stuff and in many ways running the same kind of code to generate themselves. These 2 are actually running Panda 3D. The previous games were written before Panda 3D came to be, but it's the same technology that eventually became Panda 3D. Now I keep throwing around the word game engine. Panda 3D is a game engine, or sometimes called a graphics engine. It's just a program to assist you in writing games. Panda happens to be written in C++, which is a good language for writing real fast, hard-to-metal stuff. But it has Python bindings. Python is a more friendly language. It's easier to develop graphically in Python. That means that the game developer is mostly programming in Python, and it's just the engineer who has to work in C++. And that means that you can write your programs really fast. One of the key things that we're working on with Panda was to make it really, we're really aiming for rapid development. We want to make it easy to use, make it easy to do prototyping, and even use the same thing to ship your final game. In fact, Toontown and Pirates online today, almost all that code is written in Python. People are surprised by that. But it turns out Python works pretty well, especially when you have C++ to do all the heavy lifting. That's why we get excellent performance on all sorts of computers, even your little $300 Asus, it works just fine. Now, Panda is released as free software. Disney does not claim any proprietary rights to it. A lot of people were surprised that we can do that. It turns out we successfully argued that Disney is in the business of making entertainment. We make stories, we make games. We don't sell game engines. So in fact, Disney does pretty well when people adopt Panda and use it for themselves because as people in the community are using Panda, they're contributing back to Panda. And it helps Disney as well. We've gotten all sorts of contributions, both in code and also from people who came to our, we hired new programmers who already were experienced with Panda. So Panda really is free in every sense. And no strings attached, we really do want people to use it. So for the record, if you want to write your own game, recommend it. Suppose you do want to write your own game. Where would you start? You got Panda, all right, that's good. But what else is there? A lot of people ask me this question. This, of course, depending on the size of your game and your budget, if you got a budget at all, there might be a number of different people that are working on a game together, and there's certainly a number of different roles. Now, if you have a very small game, you might have one person that does all these roles. That's not uncommon. If you have a medium-sized game, you might divide the roles up among a handful of people. If you have a really big budget game, you might have lots of little different parts as you specialize each of these roles for very specialized people. It's kind of like the way that the independent film studios work with just a handful of people doing the major pieces, or in major studio productions, you have hundreds of people working together on all these different specialized parts. But the first floor, I think the most important fundamental parts, and most of these are going to be answered in one part or another by some of your members of your team. So I'll talk about each of these in particular. Of course, it starts with the game designer. The game designer is probably the most important role, and also, I think, the most often shared among all the members of your team. The game designer, of course, has to decide what the game's going to be, and that's not always easy to do. But of course, you've got the standard questions you might have to ask yourself carefully, and basically the bottom line is the game fine? And sometimes you're not even sure of that until you got the game written, and then you go back and realize you made a few mistakes and go back and fix it. That's a common thing to do. But everybody at some level is a game designer, I think, and everybody who's working together on the game has contributions towards this part of the role. Now, suppose you decide you want to make a pirate game. You'll need to have some pirates. So that's where the modeler comes in. The modeler is a person who has the talent for making 3D sculptures in virtual worlds. And they'll typically use software designed for this purpose. This is a Maya window. There are other programs that do the similar thing. Softimage is similar to Maya. 3D Studio Max is a little less expensive. Blender is free. They all serve the same purpose in this extent. The modeler will works kind of like a sculptor. It's a lot like sculpting clay. It's a similar skill, except instead of actually getting his hand through, the modeler is moving vertices around the screen. So the modeler's job is to put all the vertices where their pirate belongs and not the vertices where their pirate doesn't belong. After he's sculpted his pirate, he'll paint it typically, giving it color and texture. And of course the modeler will also make all your props and your environments and other parts of your world. Now, when the modeler is done, the output from Maya and the input to Panda is a file that looks sort of like this. This is just an excerpt of a much larger file. And of course, it just looks like a big table of numbers. It doesn't mean a whole lot to a human. To a program like Panda, this lists all the vertices that we're just looking at here. Each of these vertices has a particular position in space, and that's described here. So this is relevant to the program that's going to load up the model and display it later. Now, once the modeler is done with the piece, you want to bring it to life, and that's where the animator comes in. Animator works kind of like a stop motion animation, or claymation, if you're familiar with that, of course. One of the advantages that a computer animator has over stop motion, traditional stop motion, is that he doesn't actually have to pose every single frame of animation. Typically, he'll pose just the extremes of motion, the beginning and the end of the sequence. And the computer software is able to fill in the gaps, which saves a lot of time and allows for much richer animations, given the same amount of time. Let's see. Again, similar to the modeler, the animator produces an output file, which might look like this. Again, just a table of numbers, but this has particular meaning for Panda. Again, this describes the particular angles and positions of every joint for every frame of the animation. And again, this is an excerpt of a much larger file. Now, we get to the showcoder, and this is the person who actually gets to see things start to come together, because the showcoder is the person who's going to take the pieces designed by the modeler, animated by the animator, and write the code, the program instructions that actually assemble this all together and make it into a game. Of course, he's going to follow the advice given to him by the game designer, whoever the game designer or designers might be. And he often is one of the game designers as well. Here's some sample code. This is, again, an excerpt of what might be a much, much larger program. But this would be some code that would possibly load up the model that we were just looking at and improve the scene and start playing. The showcoder would also write code that would basically just define the cause and effect rules of the game. For instance, you might say, you write the code that intercepts the F1 key and makes it so that when you push F1, your pirate brings the sword out and swings around. Also makes the rule that if somebody happens to be sitting in front of your pirate that does that, he'll take your head and take damage. The showcoder is the one who's bringing together all the pieces together. So just as the actor, or the modeler and the animator were working together using Maya as an artist tool, the showcoder is using Panda as a technical tool to assemble the program together. And Panda is just a tool. It provides various pieces of the things that are very important to making a game. It doesn't make a game itself, of course. It's still up to you. And the showcoder is going to be enabling physics in such a way that makes sense within the context of the game. It'll turn on lights that he thinks is appropriate, or the designer, the art designer might think is appropriate. Plays back the animations when they should be played back. Panda will do these things once you start them doing, but it's up to the showcoder to actually bring them to happen. Do we get a video? Oh, we do. Oh, no, we don't. Oh, shoot. Well, okay.
Go PowerPoint.
Well, if there were a video there, you could see it actually happen. But you can imagine when everything's all together, you get the 3D view with the pirate standing in the world, the environment all around you. It's all very rich. The thing to keep in mind is that all of this work is a result of lots of people working together, the modeler and the animator and the showcoder finally bringing it together as one scene. Panda provides the pieces that actually makes it happen. There's some technical things that happen in the background that you may not be aware of. For instance, we all know that when we watch a movie, we're really seeing a series of stationary pictures being projected in front of us in rapid succession, so it looks like motion. It's a similar thing with computer-generated graphics. Panda and your graphics hardware are actually generating the scene that you're looking at in rapid succession. It has to generate 30 or maybe 60 frames per second. And that means it's going to clear the screen, draw the entire scene in 1/60th of a second, and then do it again. Clear the screen, draw the scene again. And it has to compute that scene in real time. And the scene might contain 100,000 triangles or more, little tiny triangles that make up the little pirate, the environment all around you, all the pirates that you see. So it has to do a lot of computation. And just, if I could show the clip playing, you really could appreciate all the computation. Of course, one of the big advantages to having a computer that's doing the computation is that it means it's all interactive. It's not pre-baked. And you can change the world as you're moving through it. And that's, of course, the key point of interactivity. And it means that the last person, the last piece of the equation of all the people we've been talking about working together to make this happen, the last person is the user, of course, at the game, at the computer, who actually steers the actions in the game. So that's a little bit about Panda, a little bit about game design and making the game. And now I'd like to process may be very similar to what I just described. So, thank you.
We kind of need our video, so we're finding them now. The pirate looked really cool, by the way. Cool.
So one of the things we did first was when we were designing this game, we wanted to come up with some sort of a backstory. The whole idea with the design here was that we did not want to do your standard arcade style, just get the high score or just aimlessly go through a level without any real point. So we wanted to create a full universe that the user can interact with. In order to do this, we created basically an alternate reality. This would allow us to tweak anything that maybe wouldn't work in our own reality, so we could really have some freedom with what we would put in the game. We ended up creating really a history of the future because our game starts about 300 years in the future. We didn't want to just dump you straight into that without any real explanation. So at the beginning of the game, we spend about 5 to 6 minutes building up a story, building up this universe, explaining to you what has happened in these last 300 years. We've also put an emphasis on trying to keep it somewhat real. You'll see a lot of sci-fi games have things like shields and plasma swords and stuff like that. And while that's awesome to play with, we didn't really want to go that route because even within 300 years, we thought it's probably stretching things for what we were really going to pull off. So we do have things like spaceships, we do have more or less laser guns, but we haven't gone as far as some other games would have. Also, a huge element of our story is just try to keep it as open as possible. You'll see if you actually kind of sit down and take apart the opening story, there are plenty of gaps where if future generations have seen the Capstone project and as future generations want to come back and start adding on to the story, they are more than welcome to. There are plenty of places for them to do it. Even to the extent that at the end of this game, we essentially start a war between ourselves and an alien race. And you can go wherever you want with that, so your future computer science Capstone guys have fun with it if you really want to. With that, I'm going to let you guys describe how the levels have gone out.
Alright, so with every game we also got to have levels. We designed the game to have missions. We wanted to logically bring the player through the game in such a manner that we could immerse the player well enough into the game that he's really engaged with the concept, understands the game, and really feels a part of it. Also, we obviously had big time constraints. You know, most people know games take years and years to make, most games, and we only had a semester and a half, really, working on this game. So we designed the game only have 5 levels. We thought that was a good amount of time to get the player involved, get him learn how to fly, and we slowly moved him through the progression of the game. Now, we also wanted to design it so, as Ben said, we didn't just want to throw you into the story. We kind of, I think without a better expression, to hold your hand into the game, you know, kind of walk you through the door. And we do a pretty good job of that in this game, I think so. We really kind of just walk you through the first part of the game. So this is actually one of the first concept art I did when we were doing the design process of the game, figuring out how we were going to lay out these levels. We start right here. You start off on Earth, you're test flying a pod, and we teach you how to fly the ship. We make you fly through some rings. We show you how to shoot the guns at some stationary objects and whatnot. Basically just teaching you how to play basics of the game. Level 2, you pop out of this portal, and you start your first simple combat with the enemy as you see it right now. So basic combat, we're still teaching you how to play. That level's designed to be not that hard, even though it actually kind of ended up being a little difficult. So then level 3, we have even more complex with the flying. You have to evade. There's no way you can win mission 3 by fighting, so you have to evade. So it's even more making flying more complicated. Then level 4, we actually have this really awesome level, hopefully you guys get to play it later, that you have to fly through the asteroid belt. So not only do you have these big stationary things that you have to fly through, but you also spawn smaller asteroids that you have to dodge and whatnot. So even more, this level is probably the epitome of difficulty in flying. Then we have the very last level, which actually isn't finished yet. Sadly, you guys won't get to play it. But this is going to be the biggest battle ever. We're going to have battleships from both sides fighting. You have to fly through, you have to engage both ships, defending yourself, and try and get to the goal at the end of the level. So this is probably the culmination of combat with flying and everything else. So that's pretty much the layout of our game, and I think we're going to give the presentation through levels, and then we'll expand on it. AJ's going to go with that. Whoa. Okay.
All right. Well, that is a video, so let's open up the first one here.
In fact, it doesn't seem to be sending or receiving any information at all.
Voiceovers in the game.
Must be on autopilot. Hey, I'm going to go ahead and give you investigative clearance. I'll put it down shortly.
Okay. Let's see here. Okay. This is level 1. This is a little bit more concept art that Roger put together for us. And essentially what happens is level 1, this is our obligatory tutorial mission. We've got to try and teach you guys how to fly the ship. We do have 2 different styles of ship flight, and Ben will describe those more in detail when he presents next. But what we do have is we ask you to fly through in stabilized mode first using these 4 rings, and we ask you to fly through those rings in order to get a little bit better idea of how to fly in stabilized mode. Then we do ask you to switch over to what we can call inertial mode. It's a little bit more strategic, and fly through another set of rings. All this time, Spaceman is kind of beginning to let you know about what's going on in the game. So when you finish through the 8th ring, you do see a trash pod, and Space Command tells you this trash pod is out of its ordinary lanes. We need you to investigate this and find out why it's outside of its designated lanes, and it does give you permission to follow it. In fact, it wants you to follow it. You have to follow it through this portal. Now, as you can see, there are asteroids in the way, so this is where you kind of get the idea of this is how I shoot, and this is how much damage it's going to take to kill some things. And essentially, you're just following the pod.
Now, as AJ just described, we have 2 different types of flight mechanics. We made this decision because originally we were thinking, well, we played a lot of arcade games and we played a lot of space games, and generally what happens is they put you in space, but they give you flight mechanics that mimic flying an airplane. Isn't quite accurate. Then we've also played simulator games where you're actually in space and you're thrusting all over the place, and it's neat for the realism, but it gets really frustrating as a game. So we decided to kind of go with the medium. We allow the player to fly in the airplane mode, what we call the stabilized mode, for most of the time, but when they want to, they can switch into what we call the inertial tactical mode. Essentially, what this kind of looks like is if you ever played Asteroids, it looks similar to that, where you have simply a forward vector, and you're going to continue moving on this vector, and you can modify that as you wish, but you can pivot off of that vector. So essentially what this would look like is you're moving straight ahead, but now I can move all around and target whatever I want to. We do actually have joystick and mouse controls used for this, and when we started implementing this, we found an interesting problem. It's a problem known as gimbal lock. And I'm going to attempt to explain this to you. Gimbal lock occurs because of this situation. We have these sets of what are called gimbals. Essentially, what a gimbal does is it describes the rotation of a body about an axis. We have 3 gimbals here, one which would represent the ship's heading, one which would represent the ship's pitch, and one that would represent the ship's roll. Heading, pitch, and roll. Heading is simply where you're facing, pitch is how much up or down you are, roll is how much to the side you are. Normally there's no real problems with modifying these. In this picture you see we've made the ship change its heading a little bit. The pitch gimbal has moved slightly, and everything's fine, there's no real problems. However, we get an interesting problem when we move the heading, in this case, all the way 90 degrees. So essentially what has happened here is now we go from having a separate gimbal to control pitch and to control roll, to where now those two gimbals have meshed together. Essentially what this causes is you lose a degree of freedom. In this case, you can no longer roll, because any changes in roll will be equivalent to a change in pitch. To give you a little more finite example of this, I have, fortunately this is only a 2D gimbal, but I think I can illustrate the point pretty well here. We have a gimbal here that's going to represent. I'm sorry, that's going to represent our pitch. Three gimbals. We have roll, we have pitch, and I'm going to be the third gimbal that we need. We have heading. So if I roll my ship 90 degrees, now any change that I make in pitch, as you can see its wheels moving back and forth, is the exact same thing as if I was to take and change the heading. On top of that, I no longer have any way to make a change of pitch. So we lose that degree of maneuverability, which in a 3D space flight simulator is a big problem. So there are several ways that exist to combat this problem. One way is to use rotational matrices, and another way is to use quaternions. Both of these, I hope you guys pay attention in linear algebra, because this is all this is. So our first attempt was to use a matrix. This was before we knew that Panda had a built-in matrix, so we actually started making our own matrix class. And we were pretty comfortable with doing this method because we have paid attention to linear algebra. We're in math. So we were going to go with this, but about 2 weeks in, we're still coding, and we're still figuring out problems. And Dr. Warford finally got on us for taking so long to this, and he says, well, why don't you guys check out the quaternion? And so essentially we go from, and this is just an itty-bitty snippet of the code we use. There's no rotational matrices in this yet. All this is defining how a matrix will multiply and setting the matrices up. There's a bunch more code that went into this. But all this code got reduced down to this.
Thank you, Dave.
Yes. Learn your API, check out what your engine can do, so that you don't waste tons of time on something that is literally 3 lines of code. Oh, I'm sorry. For those of you who don't know what quaternion is, my bad. A quaternion, essentially, instead of having to define rotation as, okay, now we're going to rotate this gimbal, and this gimbal, and this gimbal, it allows us to just say, okay, I want an arbitrary vector in space, and then rotate X amount around it. So we no longer have the problem of the two gimbals colliding with each other. Sorry.
All right, video number 2. Okay, this is chapter 2. We called it Unpleasant Surprises. We've labeled each one of our chapters something. And what happens in this mission is you've gone and you've now followed the pod. It has flown through the portal. You have followed it through the portal, and you are still following the pod. And you are tasked with staying as close to the pod as possible, because you are trying to decide where it's going. Once again, it has been declared outside of its usual lanes, and as with all government agencies, we want to make sure that everything is working properly. So what we do is we have to follow the pod. Now, the benefactors, our benefactors, the people that came and saved us, have put out enemy fighters, and they are attacking us. And we need to, this is again our demonstration of this is what you need to do in order to fight. And you do kind of get a little bit of an idea of how to fight in inertial mode and use yourself as a turret, as Ben described. But they do come after you. At the end, if you do make it to the very end, which it is difficult right now, I'm not going to lie, it's very difficult. I don't think any 3 of us have ever finished it. But
So good luck later.
Yeah. You do get to the end, and you are captured. When you are captured, you are thrown into the benefactor's jail. They have a jail set up, and you meet the Guardians. You meet one man who is part of the Guardians, and he has managed to put together a video of everything that the benefactors are doing. I'm not going to ruin the entire story for you, so I'm not going to go into that, but he does help you escape, and that's where we move on.
All right. So we just talked about we actually have people engage you. It's a big problem with what we had to write. So we actually had to come up with artificial intelligence to simulate an enemy ship that's fighting you. As I said, that is the solution. So we have to write code that does simulate an enemy ship flying at you. Approaching this problem is vectors and angles. If we haven't talked about vectors and angles enough, there's more. So if you took linear algebra or are going to take linear algebra, pay attention. Because, seriously, we realized in this project that linear algebra was seriously everything we were doing. Whether we're talking about 3D graphics or talking about manipulations in space, it is all vectors and angles in computers. So it is very important. So our artificial intelligence. In Panda gives us access to setting orientation with set HPR and setting our velocities and stuff like that. That's pretty simple. We plug that in ourselves. Changing the orientation of the model is pretty simple. But the problem is, how do we make a ship go towards a location that we want to? How do we make, how do they make guidance systems and things like that? Is we have to write our own math to actually make our ship fly. So, taking our AI and basically slimming it down just to flying towards a location, we actually use this function called lookat that Panda has. We actually spent a lot of time, again, trying to figure out all this math, cosine rule, how do I get to a point, all angles between vectors and stuff. And then we realized Panda has the lookat function that tells us where we need to go, how to change the orientation of our ship to look at something. It's like, oh great, a week down the tubes, now it's one function. so what we do is we take this lookat function, take our original heading, and then take a percentage of that and slowly turn our ship towards its intended target. It really ends up being not that difficult. Here's an example of the code. We have a task that runs our ship flight. We get our ship's HPR, which is his heading, his pitch, and roll. We calculate the lookat. We set him back to where he was originally looking. And then we take some percentage of that. This is all kind of other code that's kind of not important, but it is important. It's making sure it's on the same side of the circle, because we don't want him to turn all the way this way when he can just turn this way. Shortest distance, really. But then there's the other problem. Okay, so we got the ship turning, and we have him flying to where we want it to. We need him to shoot now. This is a video game. Things need to shoot, and we need to shoot back. So we actually had to write our own code that does predictive movement, because the AI doesn't know. Because these things are moving around in three-dimensional space, we don't know where the player is going to be. So we actually have to write our own more fun linear algebra code to figure out where he's going to be. So our artificial intelligence takes 5 variables into account. We aren't actually, plotting his movements and figuring out how he's going to turn next, but we're actually just calculating where he's moving. We use these 5 things to, estimate where he's going to be. And here's our example code. Essentially what we do, without going into the code, because even this is just like, I commented out a whole bunch of stuff. But all it does is it creates a temporary position out in front of a ship and estimates kind of where he's going to be, given his last frame's position and his this frame's position. Then uses that delta with respect to how fast bullets are moving to estimate how far in front of him we should then turn the ship so we can fire our guns. I hope that made sense, because it did make sense to me. But it is actually, it's linear algebra, because it's just vector multiplication. That's really all it is you take how fast he's moving, multiply that by a speed, and that's really all that's going on. And this is more code. Down at the bottom, you see that we have these rand-int functions. What actually happened is we wrote our AIs, and then realized that our AIs were shooting too good. Our AIs were never missing. So, we actually had to add a little bit of randomness to the node that he's predicting where you're going to be, so he actually misses. Even with the randomness right now, he still hits you way too much. So yeah, it's actually a really interesting problem that it's really easy to make the AI always hit you. It's harder to make him where it's playable and fun, because that's the reason we make the games, so it's fun. So we have to tune the AI to that. All right.
Alright, that's a little snippet of level 3. So this is level 3, and the idea is here is you've just escaped from the alien jail, and you're in kind of a beat-up ship, and you're just trying to run. As it was mentioned earlier, if you try to engage or try to actively fight your enemies in this level, you will die. It is a guarantee. We actually just saw in the video you have that huge battleship coming after you, and that was actually an older video. The newer version, he's not firing these little guns, he's firing shells. And so you have to run. He's also spawning up little AIs that are coming after you. And essentially what we've done here is giving you an opportunity to use that inertial mode that we've established before. Inertial mode in general is kind of a pain to just generally fly around in, but in this case it's beautiful because your goal in this level is simply to get to the asteroid belt. So you can point yourself at the asteroid belt, kick your thrusters into full gear, go into inertial mode, and then turn around and fire at whatever's coming at you. Essentially, you just become a really fast-moving turret. Now, because the AIs predict your movement linearly, you become an easier target for them. So it is a good idea if they start getting too close to start moving around a little bit. But that's the basic overall idea of this level. It's just run away as fast as you possibly can and don't die.
Right. It was about this time when we ran into a little bit of a problem in our development. We had been focusing so much on features and just getting more features into the game because we were so pressed for time that we forgot to clean stuff up. We forgot to make sure the AI were actually deleting, and when they died, they wouldn't keep flying around. And so if you were to try and exit to the menu, you would see this AI that would fly across the screen. And that's not supposed to be there. So we had to figure out why are things not deleting properly because we thought we were doing it correctly. Why are things not going away? Well, we got into a big fight with Python's garbage collection. Now, Python has automatic garbage collection. You would think that that would make it really nice and really easy to use. We've run into a lot of problems. Python's garbage collection can be summed up in 2 words, reference count. That's it. But I wish it were just that simple. It's really not. I'm going to try and keep it as simple as possible because it is complicated. But there's no guarantees here. So these over here are just blocks of memory, and if we want to create an object, now in Python, just about everything is an object. So it becomes very difficult to try and keep track of what we need to get rid of. So what happens is in Python, if we say A gets 3, or 3.4, excuse me, 3.4 is created, that's the object. 3.4 is the actual object. A is nothing but a name or a reference to the object, or where the object is located in memory. Keep that in mind because that's really important. So, if we were to say B now gets A, we could create another name for the object, 3.4. As you can see, there's a couple of arrows that are now going to 3.4, and 3.4 is reference count, the object 3.4. Its reference count is now 2. So, one more quick example here. If we have a list and we say list.append, append, for those of you that have looked at Python, is a native Python function. We don't have to write our own, which is really nice. That's one of the great things about Python. But if we say list.append A, again, index 0 of list now is nothing but a reference to the object 3.4. So we have now 3 references to 3.4. So how do we get rid of these? Well, we can ask it to say delete A. But unfortunately, that doesn't work. As you can see, the name A has been deleted, but the object remains in place because there are still 2 references to it. So we have to get rid of those as well. B gets 7.4 will cause the reference count to decrease because B is now a name for the object 7.4, and it no longer points to 3.4. Then, if we ask list sub 0 to be 2, that gets rid of the last reference count, and at that point, 3.4 is actually deleted. So, this sounds great. It sounds really easy, right? Well, the problem is Python only deletes an object when its reference count is 0. And we had a lot of problems with cleaning up because we have a lot of references to a lot of different objects inside of our code. So the solution was to make sure that each one of our classes actually removes all of its references. And we created a cleanup function for each one of our classes that does that. This here is one of our classes. It keeps track of the most commonly used objects. Those commonly used objects are missiles, bullets, AI, the comets, and the asteroids. And each one of those has an is-dead attribute. That's how we decide if something is no longer in use. And then the entity manager can go back and clean it up. So what the entity manager does is it has a list of all of our commonly used objects. And those objects we have taken great pains to make sure that in the rest of our code it is not referenced. So the entity manager is the only thing that is referencing that code. Then what we say is we look at the isDead attribute of each one of those objects that the energy manager is keeping track of. If the isDead object, if the isDead attribute is true, we ask it to call its cleanup function, then we remove it from entity manager's list, and then we delete the reference that we've created to it. So this is what the entity manager, this is actually pretty much everything that the entity manager has to do to make sure that things are getting deleted properly. As you can see up here, x gets entity manager.list. We're actually grabbing single objects out of the list and giving them x. Now, this means that the energy manager, that list has a reference to the object, and x does now as well, so that its reference count is 2. Then, we look to see if its isDead attribute is true, and as you can see, missiles and missiles are a special case. We actually have a little bit of a difference there between missiles and some of our other classes, which is why we need these two different, this if statement. But what happens is we ask it to clean itself up, which means that it gets rid of all of its references to every other object that we might have added referencing. Then we say entity manager.list.remove. This gets rid of the entity manager's reference to that object. So now its reference count is 1. If we did not say delete x, then that object would still be flying around because it still exists, because its reference count is still 1, which is why we have to say delete x. And that essentially is how we dealt with part of the cleanup problem. A lot of the other classes we written, we had to make sure that we were going through and making sure things were specially deleted. But for these commonly used objects, this was a really nice way for us to make sure that they were getting deleted properly and the AI was not flying across the menu screen.
Which brings us to level 4, which is...
Are you working? Oh, no. Oh, no. Videos. Try clicking it? Thoughts me.
PowerPoint. This is the asteroid belt. All right, so we've made the asteroid belt, and now your challenge is, of course, to fly through it. This is easily one of the most fun levels to play, just because it is insane. You have essentially your goal is to get from one side to the other. It doesn't have to be a specific point, but just from one side to the other, and while avoiding all these asteroids. And the way we've set this level up is essentially you have these huge comets that are kind of just sitting around, not doing much, but they're huge. And then we spawn up a bunch of smaller asteroids that are flying straight at you, that you've got to dodge. And if you do not dodge them, you will die. We have abandoned the idea of, oh, we can shoot the asteroids and they'll blow up. No, if these things hit you, you will die. So you get really, really good at evasive maneuvering very quickly. Also, we've designed it so that if you try to be a smart aleck and fly to the outside of the asteroid belt before it's time, you will get killed by one of our battleships or by one of the enemy AI. It's just going to happen. So yeah, this is just simply a segue from the runaway of level 3 into the intense battle scene that's going to be level 5.
Okay. So, we talked a lot about other stuff happening, and we didn't talk about collisions that much, but now we are. Okay, so we need a way to figure out when things collide with other things. It's very important in a video game. We need to know when lasers hits an enemy player. We need to know when missiles collide with stuff. Well, Panda gives us an access into collisions that happen between things. It's pretty easy to set that up in Panda. But the interesting thing is, Panda doesn't know whether one piece of geometry is a missile or another piece of geometry is a ship or whatever. It knows none of that. All it knows is geometry. So we have to code that in ourselves. So we created this class called Collidables. Everything that needs to be collidable in the game, you have to inherit off of this class. and call its constructor and whatnot. In the constructor, you pass your reference and your type. Again, as AJ said, this is an example of us passing reference counters around that we have to clean up later. And if you forget, it won't delete itself, and bad things happen. So what we do is we create this, let's go back. We have this type. So we have 5 basic types in our game. We have bullet, missile, cockpit, ship, and other. What happens is these get put into a double dictionary where we can access them through a unique identifier in their type. This is an example of the constructor. It assigns a bullet a unique identifier. It puts its ID into the class reference, so the class actually knows its identifier now. And then it assigns it to our dispatcher's double dictionary with its unique identifier. This unique identifier stuff is important because now we have this collision dispatcher. So now we've set up this data structure that when a collision happens, we can somehow have access via the scene graph with that object. So we know which object collided, and now we have a unique identifier in which we can grab it. So, of course, we have this double dictionary here, if you've seen dictionary setups before, where the first key is its type and its second is unique identifier. When a collision occurs, the collision dispatcher compares the types and then calls respective functions, because it is important that we handle, a bullet collides with a player, or a missile hits an AI, or you drive into a comet and your ship blows up, which is very important. I'm trying to compact this because we're running out of time here. So this is an example of the collision dispatcher code. And actually, what's kind of funny is we wrote this whole collision dispatcher again and didn't read the API. And so we wrote this whole thing, and we check its types, cockpit, other, and then we go into this double dictionary that we set up. What's actually interesting is we didn't realize at the time that Panda had a function called setPython_tag, which will actually set a memory location reference onto a node. So we could have just said node.getClass, and so a ship would have known it's a class. But we have this now. And it works. So we don't have to rewrite all that. So as you can see, we check if it's a cockpit, the thing that you're flying around, and if it collides with another being like an asteroid, the trash pod and stuff like that. And it calls the respective function in the game manager, which then calls the functions inside of the class, whether, if you drive into an asteroid, you blow up, or
Chapter 5 is our last chapter, and we don't have a video for this chapter because it's not completed yet. We're still working out a couple of the kinks. But essentially what happens is this is the biggest, nastiest battle that we could possibly imagine. We have very large battleships, as you saw in the video for Chapter 3. On both sides firing each other, the AI and the Guardians and the benefactors are fighting each other, and so there's just mass chaos going around. And you have to make it from one end of this mass chaos to the other to get to the satellite and send out this video link that the Guardians have managed to get to you. I'm going to cut it off there because we're running out of time.
Oh, it worked!
Okay.
Man, goodness gracious. Look at those 6 slides within one click. Okay, so, as Dave talked about before, we have the problem of art. Our solution was, we were trying to find an art major, someone around campus that could help us, or maybe someone off campus. The problem ended up being artists are expensive, and artists don't want to work for free. People don't want to work for free. So I ended up doing the art. Programmer art, but it actually ends up looking okay. So I was going to talk to you a little about the art pipeline, because we are running out of time. So Panda 3D, as Dave talked about, gives you some way to render stuff that you create. The problem is it doesn't give you good tools. You can make the geometry yourself, but it doesn't give you real pretty tools to set up, the geometry and stuff. So we decided to use Maya, as Dave's screenshot showed, to create these models and create the geometry, to paint them, etc., etc. So the pipeline is basically thus: we create the model in Maya, we create the geometry, texture it, we add the collision geometry there, we convert it to the Pandas 8 format, which is the native format it used to load it, and then we convert it to the BAM file, which is binary, it's fast, it's small, lean, mean, etc., etc. Then we can load it right into the game and move it around, orient it, do what we need to with that model. So let's use the example of the cockpit. As you saw in the videos, you were actually inside that cockpit. We take the camera and stick you right inside of here. As you can see, this doesn't look much like a cockpit when you're outside of it. But when you're inside of it, it actually looks pretty good. As you can see, we got our screens here. And if you look on the right, that's actually a sample of what the scene graph We didn't talk much about the scene graph, but it's pretty pivotal to how Panda works and how everything works. But that is a layout of the geometry of how this works. The reason we don't just lop it all into one big node is so we do have access to each part if we needed to move it around, etc., etc. And the most important one, I think, with the cockpit are these black screens. You don't see them textured right now, but they are important later. Here's another view of the art of the cockpit inside of Maya. We got the wireframe model, the lighted model, which doesn't make any sense, even though there are bump maps. And then the screens, and then the flat shaded model. So then we add the collision geometry. I'm not sure if you saw in the game, but we do have 4 different areas in which a ship can take damage. With this came a little bit of complication in the code, but it actually, I think, makes for a better game because you don't just have a global hit points. You actually have you can blow off a wing and lose that way. So we create these collision spheres these are what Panda uses to tell whether or not stuff collided. You don't see these in game, but it is actually what's being used to calculate collisions. So this is an example of the A file, the vertexes and all that good stuff. And then the binary format that you can't read, but I think that's good for explanation. And then you see it in game. So this is that same thing that was in game. We have, and then remember those big black screens I was telling you about that were here, here, and there? We've actually taken those and we procedurally texture those in game. So we have, things to show your speed, to show the radar, the energy for your guns, or your 2 targeting screens. This is all done procedurally. So we actually have to go in and do some magic with off-screen buffers and take that and paste the texture onto those screens. But this is pretty much the pipeline that we use to create the game. So with that being said, we're pretty much done. I'd like to give a special thanks to Christian. He helped with a bit of the art. Pretty good job. He's a way better modeler than I am. And Tyler Hayes helped me do that intro video that we saw and all the videos. Dr. Iga was helping us solve the gimbal problem before we realized there was a set quad. He didn't know either, so it's not his fault. Debbie Kim, she actually helped me with a lot of the textures from VR Studio. She taught me how to use Maya over the summer, and she's been like my AIM buddy when I have art problems. So Kevin Lambert also made all the sounds and the voiceovers. We didn't hear a lot of the voiceovers in the game, but we wanted to make sure that, even in tutorials, if you guys have ever played a game that's just text and you're going to have to read while learning how to play the game, it sucks. It's terrible. It's not good at all. So what we do is we made the voiceovers and we made Space Command tell you how to fly and tell you what to do, which makes for a better experience. And then, of course, David Rose for answering all of our problems and being our forum help whenever we need help. So if you want to find out more, you can download the game. This is our website, so write it down, play it, have fun, enjoy it. And I'd like to start question and answer period if you guys have any questions.
First question?
Oh boy.
So, the asteroids, they look like there are a lot of different kinds of asteroids. Did you model one type of asteroid and make lots of copies of it? Do you have 5 different types? Did you just kind of make it have this random thing so it's on the fly creating a different?
No, actually we have. I think we have 3 or 4 different types. And what we did, we have 2 different types of bump mapped ones, so they'd be prettier. But really, they actually are. There's no randomness in them. We actually modeled them in Maya. And the magic of making the asteroids, because I think they're the best looking model in the game. Because really, when I modeled them, I just created a sphere with a bunch of polygons, covered my eyes, and used the facial desculpt tool. Okay, looks like a rock now. Cool. But yeah, it was pretty much just simple arts.
But then what's the difference? Do you rotate them or?
No, actually we didn't. We just when we created a comment, we asked it to find a random integer 1 or 2, and it picked which one we loaded.
Yeah. On top of that, because it's kind of random looking, we can actually scale them up, scale them down. You get not only a whole new asteroid, but you get all these levels real quick. So it's a very neat way to do it.
Some of us are counters. Early in the presentation, you had the asteroids represented by pentagons, and later you got them represented by hexagons. Did you know that?
Concept art. See,
No, there's no question. You don't have to. I do have a question.
Yeah, go for it.
Did you make your acceleration real?
I think that's the difference between inertial mode. See, what you're talking about, the true physics model is the inertial mode, where whenever you thrust, then that that gives you an acceleration, and then once your thruster is off, you continue at the same.
Yes.
But that's the difference between the inertial mode and the other mode. The inertial mode is very difficult. So the other mode is more like it's not physics.
Yeah.
It's more like flying an airplane.
The biggest problem we had too is because it is a video game, we can't let your speed kind of just diverge. Because if you are flying thrust and you're in space, your speed should just go up. But because it's a video game and everything's scaled nicely, we have to kind of top out your speed at some point. So we just kind of round your velocity vector if you're turning and stuff. So we do fudge the physics, I'm sorry. To make it real.
However, you do it when you're not close to the speed of light.
No relativistic effect.
That'll be in version 2.
Yeah. Time dilation will be in Guardians Part 2. Anything else?
I have a question. David, I saw in your code you have AI Roger and AI Ben and AI AJ, I guess. No? Okay. Well, I was just wondering what's the difference between your AIs?
Well, my AI, its goal is, well, it started out as its goal was just to kill you. We kind of made a joke, it was kamikaze. So it started out just, it would come at you, it would shoot at you, and it's been refined to the point where now, if he will come at you and shoot at you, he is aware of any objects around him, and he will avoid those intelligently. And then he will, on top of having the prerogative to shoot at you, if he just kind of lines up at you and you line up at him, and he starts taking damage, he will wave off. So that's how I've approached combat.
It started off as a contest.
Yeah.
We wanted to see whose AI was better. And his is better. So, yeah, we both just have kind of different approaches to how we wanted to approach making an AI. And
So what's your
my approach is...
His has more of a pack mentality. His will fly at you and then turn around, and then fly at you and then turn around. And if you have 5 of them, they're flying at you and turning around.
Captain Irritating.
Yes.
Yeah, because his goal is like, he'll fly at you, shoot, and then turn around, and then when you stop targeting him, he'll turn around and shoot you again. So, yeah, it's kind of like guerrilla warfare. Yeah. Anything else?
Why do you guys pick a space game? Play a lot of Wing Commanders?
Wait, what?
Why do you pick a space game? Did you play a lot of Wing Commander, or was there another?
To tell you the truth, we actually started off, we wanted to design an RTS. And I think because a lot of the RTSs... real-time strategy, Warcraft, Starcraft, something like that. And because a lot of, we play a lot of Halo, we play a lot of Starcraft, we play a lot of more space-ish games, that's kind of the genre we were pulled to.
And relatively, the flight simulator is probably way easier to write than in the restraints of time.
Yeah.
It came together a lot faster than any other game. Is that it?
Any more questions? All right. Thank you very much. Do we have?
Yeah, we can hook this one up right here.
Have
If anyone wants to play.
Try your hand.
Yeah.
$5, anyone that could beat level 2.
Yeah.